Everyone, and welcome to this module on Introduction to Continuum Mechanics. In this module, we will discuss divergence theorem and we will solve some problems using this theorem. We will not provide uh, the proof as the book also did not. And we will also derive the divergence theorem for higher order, let's say, tensors. So now let's get started by a vector field. So uh, so if we have V as a vector field, so we have V1 as a function of x1 and x2, E1 plus V2 as a function of again x1 and x2, sorry, E2. So from Green's theorem, from Green's theorem, you know that the integral of partial derivative of p with respect to x dA over the domain R can be written as p nx ds over the curve, over the curve that encloses that domain. And again, here we have the partial derivative of p with respect to y dA. And here we have R again, and this becomes p and y ds c. So if I apply the Green theorem here on V, then what we get is basically partial derivative of V1 with respect to x1 dA R is equal to, then we have V1 n1 ds c, and then we have partial derivative of V2 with respect to x2 dA R is equal to, then we have V2 N2, this is dsc. So if I sum both sides of this inequality, then I get the integral partial derivative of V1 with respect to x1 plus partial derivative of V2 with respect to x2 dA over the domain R is equal to, then we have V1 N1 plus V2 N2 ds over C. Alright, so if I write this in tensorial notation, so in indicial notation, I get partial derivative of Vi with respect to xi dA over R is equal to Vi Ni ds on the curve closest domain R. Or in tensorial, in tensorial format, this is the divergence of T d, oh sorry, this is the divergence of V dA over R is equal to, and this is V dot n, because this is a scalar, so V dot n ds c. And you know that basically divergence reduces the order of your tensor by one. So if V is a first order tensor or a vector, then it gives us a scalar value. So we can basically extrapolate this pattern here to a three-dimensional domain like the volume and surface. So we can simply write the integral of the divergence of V over dV, or V, and V here is volume, is equal to V dot N D, and this is capital S. I'm gonna write it like this to distinguish between the small s. So we have over S. So even you can write these equations having a scalar value multiplied by v. So if alpha is a scalar value, then you can even write this as the divergence of alpha v dv over v is equal to the integral of alpha v dot n ds over s. We can also write this for a second order tensor. So for a second order tensor, we can write this as the divergence of t dv over v is equal to the integral of t n ds over s. And if you write this in initial notation, we have the derivative of tij with respect to xj, because this is going to give us a first order tensor. So our vector dv is equal to, then we have tij nj ds over s. All right, so if we go for a third order tensor, then we're gonna have the divergence of, let's say, tijk over xk, because this is going to give us a second order tensor. dv over v is equal to the integral of, then what we get in here, tijk nk, because this is going to give us a, let's say, second order tensor. So this is the s over s. So you can write this for fourth order, fifth order, and so on for any higher order tensor. Okay, so now let's solve the examples. So let's get us started by the example 7.2.1 to appreciate the concept of divergence and some other concepts in here. So here we have an equation that says that the resultant force, where we know that is a vector, is the integral of the divergence of t. So the stress tensor, for example, you have in here the Cauchy stress tensor, dv over v. So to prove this, we know that F is a vector field. And it's basically, if we disregard the body forces, we only have the traction forces. So we have T, the traction or the force vector, and we integrate this over the surface that we have. So here we have the capital S, and then we have S in here. So if I replace T by capital Tn by its definition, then I get this value, and I can replace this with the divergence of T dv over v. This can be also written as in additional notation, fi is equal to, so it's the divergence, so it's tij with respect to xj, because this is going to be a vector field, or first order tensor dv over v. So you can simply see here that the resultant force is equal to the integral of the tractions over the surface. So next we have example 7.2.2, and here we're talking about the resultant moment. So basically we have the equation as the resultant moment with the capital M here, x cross t or let me just write first the whole equation here. So it says that m is equal to uh, the integral of x cross the divergence of t plus 2ta, where we know that this is the dual vector of, let's say, the dual vector part of some kind of, tensor that we have to find. And then we have here v, and this tensor is here is t. All right, so we're going to find this equation here. So we know that the moment is basically the vector that, so it's the arm vector x cross t here, ds over s, and here again we neglect the body forces, so we only have the tractions or the force vectors, and we are going to integrate this over the surface domain. So then we have the integral of x cross tn ds, because we already replaced t with tn, over s. So if you write this in, let's say, the initial notation, then what we get in here, we have xj cross, this is a vector, so we have t n k, right? So then we have mi equal to the integral of xj cross t n whole k ds, because this finally is going to give us a vector. So we put k in here. So if I do the cross product, then I'm gonna get ei, then I'm gonna get epsilon jki, then I have xj t n k ds over s, where I'm going to write this t and k as, so I have ei epsilon, and this jki, so we know that we have ijk, and it is positive if we basically have this direction, the clockwise direction. So then we have jki, so this can be replaced by ijk, is also equal to the ijk, then xj, and this t and k whole t and k can be written as t k m n m. And I already mentioned the reason behind just writing this as this. It's because if you have a tensor, so since we're going to multiply them together, so if it has rows of k and columns of m, because we know that the tensors, they follow the product rule of the multiplication rule of uh, of matrices. So then this is going to be m, for example, y1. So then we can do the product. So we finally get something like this. Then we have ds over s. So if we look at this, then we can use the divergence theorem in here. So we have ei. So then we take the divergence of epsilon ijk xj tk m with respect to x m, of course, because we have nm in here, dv over v. So this is basically equal to ei and whole. So we have to take the partial derivative of epsilon ijk with respect to x m x j t km, and we have the integral in here, right? So I'm gonna put the integral in here, then plus epsilon ijk partial derivative of xj with respect to xm tkm plus epsilon ijk xj partial derivative of tkm with respect to xm whole dv. All right, so this one is equal to 0 because this is either 1 minus 1 or 0. So if we take its derivative with any kind of variable, it becomes 0. So we have ei, then we have the integral, and then we have this xj, oops. So we have this as delta jm, and this only has meaning when j is equal to m. So we have epsilon I j k tkj plus epsilon I j k xj partial derivative of tkm partial derivative of xm whole dv. And if you see here, this is nothing but x cross the divergence of t. So we already found this part, and we have to find this part. So from the first module, you know that I write this with another color. So we know that 2ta is equal to minus epsilon I jk t jk e I. So using this, we can basically, if we swap here, if we swap k and j, then we get equal to ei. We have the integral of epsilon I kj t jk plus epsilon I jk xj partial derivative of t km respect to xm dv. Then this is equal to, so epsilon I kj, so if you look at here, I kj is basically minus 1. So it is equal to minus epsilon I jk, basically. So we have ei, the integral. So we have minus epsilon I jk. Then we have t jk plus epsilon I jk xj partial derivative of t km xm dv. So let me just write this down in here. So using this, and if I just shift this a bit here, and we say that swap k and j only here. So then finally we get this as ei, the integral. This is 2ta, because this is equal to minus epsilon I jk t jk ei. So this is basically, I'm not going to write ei because I already entered this ei in here. So we have m equal to, then the first one is 2ta plus, and this one is x cross the divergence of t dv over v, which is the one that we had in here. So the next one is example, let's say 7.2.3. And in this example, we're going to find an equation for the power. So we know that the power is the rate of work. So instead of T dot x, we have T dot v, because we already took the material derivative of x with respect to the material derivative of x. So that's why we have v in here. ds over s is equal to the integral of the divergence of t dot v plus the trace of t transpose del v whole dv over v. So first, we write p equal the integral of t dot v over s. Here we have ds. So if I replace t with its definition, I have tn dot v ds over s. So I can write this as n dot t transpose v ds over s. So since this is dot, I can also write this as t transpose v dot n. This is ds and this is s. So I'm gonna get, so I have t transpose dot n. So I can use the divergence theorem and write this as v, the divergence of t transpose v over dv. So if I find the divergence of t transpose v, so I will be able to write this equation here. So I'm going to write the divergence of t transpose v is equal to the partial derivative. So we know it's a vector. So this is t transpose ij vj with respect to. So this is going to give us a vector. So this is I in here, and the divergence of a vector field reduces its order by 1, so we get a scalar field. So here we have xi again. So here we have a vector, something like, let's say, ai, and the divergence of ai with respect to xi is going to be a zero scalar, zero order tensor or scalar. So then I take the derivative of, so I do the transpose, then I have ji vj with respect to xi, which is equal to the partial derivative of the first one, which is tji with respect to xi vj plus tji partial derivative of vj with respect to xi. So if you look at here, so here we have the divergence of t transpose, and this is a vector field. So it's a vector like aj, and here we have aj vj, so it's going to be dot v, it's a scalar value finally, plus here again we have a scalar value, so tij something like another, let's say, the gradient of v, so it is going to be a tensor again. And we already proved that this is equal to the trace of t transpose del v, or it's the trace of td, and where d was the symmetric part of the velocity gradient. So we can write this. So if we replace this in here, so we finally get p is equal to the integral of the divergence of t transpose dot v plus the trace of t transpose del v dv whole v.